Okay, good afternoon, everybody. Today I want to talk a little what makes the new world of mobile devices possible. And I think what I see is we want to have internet anywhere, anytime, and forever. There is now an application which you can download for the DAC 48. So if you go to iTunes, you can download an application. You can check out where are the different companies. So it becomes more and more important to have the internet available all the time. So what we need is we need more performance. We want to have less weight. We want to have increased portability. And certainly we want to have long operation times. We want to use a phone in the morning. During the day we want to do emails, and in the evening we still want to do pictures. So there's a lot of performance requirements for the physical IP, for the processors. And I want to highlight a little what is ARM doing in this area to combine physical IP and the processor IP to give you all these advantages and access for all the functions over the day. So I'm from the physical IP group in ARM, so you have maybe seen the logo Artisan Advanced Physical IP. So that's the team in ARM where we focus on developing the different products there which are important around the ecosystem for the ARM processors. So we have there the logic libraries. We have a combination of different libraries focusing on high performance, focusing on low power, and certainly also high density. So different libraries which we provide. We pioneered multi-channel libraries in 40 nanometer. We have multi-channel libraries available now for a lot of different 40 nanometer, 28 nanometer processors. Later on I will give you some details there. Multiple track height libraries, typical in the newer technologies. We have 9 and 12 track libraries. In older, which is then 90, 65, we also have 9 or 7 track libraries there. Memory is important. We have different architectures there. We have ultra high performance memories which are important for the best possible performance. We have high density memories, high speed memories, and we have a lot of functions in the memories to enable power saving for you. So there are different power down modes. And we also support low voltage operations, give additional features so that you can use dynamic frequency and voltage scaling, for example, which enables you to adjust voltage and then frequency to give you better overall energy consumptions. Power management, we have a dedicated power management kit for the standard cell libraries. This is a combination of power gates, level shifters, all what you need to maintain, to build power islands on your chip. You can shift up, shift down with the level shifters. We have different types where you can place in different parts of the on the chip, receiving or driving side. So a lot of different functions there. Power gates also, we support header or footer cells, so you can switch VDD or VSS. There's no standard in the industry, so we support all, and I think both types make sense still. Then we have processor optimization pack. I will go on this detail in the next slide, so let's focus on interface. In the interface area, ARM focuses on what is important for the ARM core, which is DDRs. So we support a wide range of DDRs, and we have GPIOs for your normal applications there. So processor optimization pack, I guess you have maybe seen on some other booths a similar slide. So some years ago, after the merger, ARM and Artisan, we looked what can we do better to enable our customers to get the best possible performance out of ARM cores. And because that's really the goal of us, you should use ARM physical IP, ARM cores together to get the optimal performance. Otherwise, we have not done a good job. So we focus on this, and as a result, we have these 3 areas. We have the core optimized physical IP. So if I go back here, we have there some special logic libraries, some special cells, and we have also some special what we call fastcast instances, which gives you optimal performance, optimal timing for ARM processor cores. There's some special tricks which we know how to use the memories most optimal, and we can tune the memories towards maximum cycle time there. Then we will give you certified benchmark information. So we will implement the ARM cores for which we developed these performance optimization packages by ourselves from the RTL down to GDS2. Then we tell you exactly under which conditions you can achieve which performance points, so that you know exactly when you implement you can achieve the same results, or maybe even better if you have some better tricks than we have. So we have some very advanced customers, and I'm sure some of them will do better than we do, but at least you know what is your minimum which you can achieve. To enable this, we give you a reference flow, we give you a user guide for the performance optimization pack, which details exactly the steps which you need to do to achieve the performance which we achieved. So it's a more good examples, maybe a cookbook. We give you exactly the ingredients, we give you the recipe, and at least you can achieve the same results. If you are a very good cook, most likely you can do something better, but that's then up to you. So the goal of all this effort is to increase the performance compared to out-of-the-box implementation. And typically we have about 25% improvement compared to out-of-the-box. So this is the high-performance goal. But we also have some customers which use the POP to optimize for lower power, because that's also important for some of our customers, not the raw performance, but very long lifetime. So we enable this both with these packages, and we have these packages available for our partner foundries. TSMC, we have packages A9 for the 40G, 40LP, and then A5 for the LP, and we start with the A9 28HP, and we work on more packages there with more processors becoming available. Similar global foundries, Cortex A9, 32LP, 28 SLP process, so their activities also with Samsung, the same processes there. So a variety of these packages available, especially for the leading edge processes, and we work on much more of these packages. So one point where we achieved very good silicon results in the 32, 28 nanometer space is the A9 POP for the Samsung 32LP process. We achieved the performance goal. We overachieved the performance goal. So we are happy about this. This is used in production now by some of our customers. So a good proof of concept for us, and we work on more packages. So the 28 nanometer development, depending on the process, is either in a process of taping out, or we would develop the physical IP. So example from the 40 nanometer world, so 40LP, and you see there the jump mixed VT, traditional out-of-the-box flow, and then if you use the POP package, and you have a performance there improvements from 750 to 870 megahertz. So that's a good typical example what we see, and some of our customers are quite happy to get this, or even less would be good, but that's the minimum that we achieve. And then you can go with overdrive, you can go higher performance points, or if you then use typical silicon speed binning, you can go up to 1.4 gigahertz. So 40LP, that's also used by our customers. Out of the box experienced, so very positive received from our customers, gives them a very fast turnaround time and enables them to bring the market, to bring the products to market very quickly. Some other examples from the physical IP side, 40LP memories. So we done some respin of our 40 nanometer LP memories. We have improvement in the area, so we tuned the memory slightly different to have area savings. So we got a better than 20% improvement over process scaling. So this gives us the most dense memories in the 40 nanometer LP space if you need this for very consumer price sensitive applications. And we have some new leakage reduction features in the memories to give you a more standby. And then different types of leakage savings mode. We call it nap mode. I know some other companies use it light sleep. I think it's on the end. I don't know what will prevail as name. So nap mode, sleep mode, retention mode, shut off mode. So different ways for you to manage the leakage power. Certainly you pay with access time, with the initial access time after wake up. Like if you wake up out of deep sleep, you need a little longer, so the memories need also a little longer to come up to speed. And we specify this for you, so it's ready to use for you. On the standard cell side, as I mentioned before, in 40 we started implementing multi-channel libraries. We continue this in 28. And what is interesting now in 28 is that you have even more different VTs. So you have, in this process example, you have 4 VTs. There are also processes where we have 5 different VTs, so quite a lot of options there. So if you simply use the VTs, you have about 40x in power variation, 2.5 variation in the performance. You can expand this with the long channel length, so you get 100x power variation, which is quite a lot. Performance still 2.5 variation, so you see long channel devices have a lot of leakage savings and limited loss in performance. And finally, what we now do and support is expanding this with different voltage domain, underdrive and overdrive. So this gives you for a very long range 200x power variation, 4x performance variation, and that's what we see used in this very big SoC designs to ensure a variety of process mode supports there. So one interesting aspect is voltage scaling, or how we see the development of voltage, and that's also an outlook to 20 nanometer where we start to work on. So if you see traditional, the green curve is, if you look from the past, with each process generations you had a reduction in voltage. We see that this, and I'm sure you see this also, that this breaks down. It started to break down at 65 and it became really painful in 45, 40, 28, and it will also be painful in 20. So that's based on the physics there. we cannot change the physics, but what we can do is we can improve the voltage scaling by providing IP with low VDD support. So we have special memory modes which enable lower VDD support below the nominal voltage, and the standard cells are built to work on a lower voltage modes. So gives you the option to reduce your voltage, which is very important in these nodes. So we work very close with TSMC, with other foundries on this to make sure we have some way for you to go to 20 nanometer without blowing out the power budget. So some examples where we got very good results, which is publicly available. There are a lot of devices where we cannot talk about the IP which is inside. We have this Sony device, Sony phone, Sony stereo camera. So this is implemented in a 45 process node, ARM physical IP, and ARM 11. So a good example where a combination of ARM IP is used, and maybe even more exciting device, Galaxy S2, Cortex A9, so ARM leading edge processor, ARM Mali graphics chip, and then ARM Artisan physical IP 45LP. So a good example out there, and I see this phone is given on, I think on the Samsung booth, you can win this. So good example of use of ARM physical IP in these advanced nodes. So to help you, and we are here at ChipEstimate, and ChipEstimate helps you to find the different IP. But if you find the IP, you need to download it because there's some licensing for IP. So you can go to Design Start on the ARM webpage to download the IP. And on this webpage, you will also find a new SoC design community blog where ARM technologists, customers will give inputs on and tricks for using the ARM IP. So some new forum for you, and I encourage you to check this out.
Any questions for Wolfgang? Here.
What DDR speeds do you support in 40 nanometer?
So DDR speeds in 40, it's 1.66.
Question?
Any plans for low VDD support for 45 nanometers? Extending it back?
I don't think so at the moment. There's a lot of processes coming in 28 where we spend a lot of effort, and I think we would need a very compelling reason. So you can talk with me, but at the moment there's no plan.
Is the 20 nanometer foundation libraries readily available now?
No, 28 is available for different foundries. 20 nanometer is in development.
Okay. All right. Any other questions? Well, thank you very much for